Hi there, my name's Chris Collison, and today we're going to finish the experiment associated with kinetics. We're going to talk about how temperature plays a role in increasing the rate of reaction. So let's jump right to it, and this is for Chemistry 155, experimental workshop in chemistry, general chemistry, the kinetics reaction, part 2. See you there.
So here we are. Kinetics of reactions. This is chemistry experimental workshop 155. And let's first start with a recap. And we remember from the first week that we're working with this potassium permanganate solution, which is purple, and we react it with the colorless oxalic acid in here. And what we find is that the products are a yellowish solution. Most people found that they had a yellowish solution in the products, and we ran 5 sets of each experiments in here. And what happened in the first set is we ended up doubling the concentration of the oxalic acid, and in the second set of experiments, or in the third set actually, we're doing a comparison where we've doubled the concentration of potassium permanganate while keeping the concentration of oxalic acid constant. Okay, and what that allowed us to do was to find these orders of reaction in here. And then when we take any particular rate and we plug in the concentrations and those derived orders in here, then we can determine what the rate constant is. So you've done that in the first instance. You've measured the rate for a bunch of different concentrations. You've calculated the rate constant. So what are we doing this week? So in part 2, we're going to ask ourselves, how does the rate change with temperature? And if we look at the rate equation that I showed you from the previous slide, what we find, of course, is that there's no temperature listed in this particular expression. So it begs us again the question, how does the rate change with temperature? And experimentally, we can observe that many reactions double the rate. So the rate of many reactions doubles when we increase the temperature by about 10 degrees Celsius. So why is that, and how can we explain that? Well, we actually use the Arrhenius equation, and this is the Arrhenius equation shown above. And what we'll find is that the rate constant in here is equal to some pre-exponential factor, that's capital A, multiplied by E raised to the minus EA over RT. The EA in here is our activation energy. So here's our activation energy. The R is simply the gas constant, and that's given in System International units, 8.314 joules per Kelvin per mole. And the temperature here is absolute temperature. So this must be in units of Kelvin. It must be in units of Kelvin. That's really important. The interesting thing here to note, by the way, is that when the temperature goes up, so when this temperature goes up, note that the exponent, or the magnitude of this fraction, goes down. So the magnitude of the fraction goes down. We have a minus in front of it. So actually, because the fraction goes down and there's a minus in front of it, then this value in this exponent actually goes up. Okay, so basically this demonstrates mathematically why when the temperature goes up, the rate constant also goes up. It's because the temperature is in the denominator of this fraction and there's a minus sign in here for the exponent. So have a think about that and make sure that it makes sense to you. So what's the goal of this particular experiment? Well, the goal is to determine that activation energy. So that activation energy, E sub A, we're going to figure that out, and also that pre-exponential factor, capital A. And how are we going to do that? Well, we're basically going to run the same experiment that we ran last week. Okay, we're going to use 1 milliliter of the potassium permanganate, 5 milliliters of our oxalic acid. We're going to, of course, add the 6 milliliters of water that we need to bring our total volume up to 12 milliliters. So this was the same experiment that you did in set 1 last week. And by the way, if you did that in set 1 last week and you found the temperature to be around 20 degrees Celsius, that's really the first set, so you don't have to repeat that this week. What we're going to do in this upcoming part 2 is we're going to start to increase the temperatures. Of course, what does this mean for the rate? We're going to expect the rate to go up. We could, of course, also bring across some ice, so there'll be some ice for you as well, and we can have a water bath where the temperature is 0 degrees Celsius. So that's something else that we can do. Of course, we probably want to start those experiments fairly early in the lab, because with a lower temperature, we're going to expect the rate of reaction to be much, much lower. It's a good idea, though, to use one of your temperatures with ice, and that will be a very slow reaction. So again, how are we going to determine the activation energy barrier, and how are we going to determine the pre-exponential factor? So, what's the rationale for doing this particular set of experiments? Well, if we come back to our Arrhenius equation, and what we're going to do is we're going to take natural logs, and the idea here in this slide is that we're going to get to a point where we can make a straight line plot and use our regression analysis in Excel to help us pull out values of activation energy, E sub A, and the pre-exponential factor A. How do we do that? We take natural logs of the Arrhenius equation. Okay, so clearly on the left hand side we're just taking the natural log of K, and we can take the natural log of the right hand side, and we're going to be able to split these. So of course the natural log of a product means we end up with the natural log of one of those components, A, plus the natural log of the second component in that product. And the other nice thing here is that when we take the natural log of an exponent, okay, we can effectively cancel out that exponent. What it's going to do is it leaves us with the exponent. We bring this down, and that now becomes a fraction. And when we now look at the equation, this equation number 5 in here, okay, and we can compare it to our typical y equals mx plus b equation of a straight line, what we find is that the y value is the dependent axis is going to be the natural log of k. The x-axis in here is going to be 1 over the temperature. That's the independent variable. So of course we can control the temperature. This is going to be and must be in Kelvin. Absolutely must be in Kelvin. Everybody, every year there's someone that doesn't put it in Kelvin. They get the answer completely wrong. It must be in Kelvin. Don't let that be you this year. Okay, and then we have a slope, and the slope ends up being minus EA over R. So our plot looks something like this. We've got 1 over temperature, and that's in Kelvin, minus 1, the units of the x-axis, and natural log of K. Okay, and that's unitless because we have a natural log in here of the y-axis. Okay, and so what we're going to get is some straight line plot in here for which the slope is going to be minus EA over R. And if the slope is negative, then EA in here must be a positive number. So it must be a positive number. It makes sense. It's an activation energy barrier which we must get over for the reaction to occur. And then we're also going to find that our y-axis intercept in here is simply equal to the natural log of the pre-exponential factor. So these are the values that we're going to be calculating in this experiment. If we go back to the previous slide, there are these 5 experimental sets. You've done one of them already, so you don't need to do that one again. You can pick 4 different temperatures. So these are the 4 temperatures that you might end up doing. It doesn't matter what those temperatures are, you just need to have different values. And the other thing in here is that you may want to have 3 samples for each set so that we can get averages and of course the standard deviations. and we can plug those into Excel. You know the drill already by now. So fairly straightforward experiment. Start the cold reactions first so you get them going. It's simple. Think about where your error comes in and put that down in your report. Think about how you could improve the experiment, even though you're not actually going to have the opportunity to improve the experiment this time around. But imagine if you were to redo it, what you would do to improve it. And that's it. I hope you enjoy the experiment. It's a very good introduction to chemical kinetics, and see you in the lab. Thanks for listening.